Okay. You know our partners, Open Table. We love them. Lamppost, Carbon 5, EPV, all these people surround us in some way and bring that pizza that is in your hands or in your bellies, that pizza, every week. We're not going to tweet it a sponsor today. Maybe next week if I feel like it. Aren't you guys happy that I'm not harassing you about getting your phones out and tweeting at people? Next week, if you're feeling lonely. Okay, Instagram, we're on there. Twitter, Meetup, you know the drill. Andrew, aka Ace Drew, continues his Humans of Chadev series, so be sure to check that out for some fun and embarrassing moments. Meetups, we got them. Check them out. All these links are clickable if you want more information about any of these. You can go to this URL that you can't really read here. Up top, chadev.com/lunch-slides is what it says. The Chadev survey, yes, something very near and dear to my heart. This was started by a member of our community, Jared, and it's a project for us to get an understanding of what's going on in our community in terms of positions and salaries and all of that good stuff. So just trying to give the people some power in terms of all that good stuff. So probably the most sensitive piece of information that we'll ask you all in this survey is salary. It'll all be anonymous. It's going to be compiled sort of like into some infographic style presentation for you all. As of last week, we had about 20 or 30 responses. We need roughly like 50-ish more in order for it to be statistically interesting and perhaps valid. So check this out, bit.do/ChadevSurvey. Go on there. We really appreciate your participation. Pass it around to other people that maybe don't come here, but also do work in the developer community. Okay, if you have any questions right now about the survey?
Should we bump up our salaries 50%? So like if somebody looks at it, they feel like this is what a developer costs.
That's probably a good idea. Yeah, that might be good. Pro tip. Okay, hit us up on Slack. We're there. We're 100 plus now. You can get your invite to our Slack channel and come chat with us there at chadev/slackin.herokuapp.com. And then our login, of course, is chadev.slack.com. And if you don't like that and you're all about the IRC, you can get on there with us too. Job board, we got the jobs. You want the jobs, they're there. Check them out. Of course, I mentioned these slides already. And without further ado, River. Give River a round of applause. Round of applause, yes. I've got a link to River's GitHub here. He's going to be talking of it today. He's going to talk to us today about cost functions. And River is currently working on
Facebook integration for a Meteor application.
All right, Meteor.
Meteors.
Holla. Okay.
Oh, yeah. This is complicated. Can everybody hear me? All right. Is this the slides? What is this? No. Okay. This is okay. Gotcha. Go ahead and do that. All right. Hey everybody, I'm River. I just graduated from UTC with a mechanical engineering degree, and I learned some cool stuff that I thought you might be interested in. Also, I've studied machine learning quite a bit outside of school, so I'm going to talk a bit about that stuff as well. So I'm going to start off by just asking, how do we make decisions in general? Like, this talk is really about making decisions in general, any kind of decision, any small decision, really complicated decisions too. So basically the process breaks down to list your options, weigh your variables, and then score your options based on those weighted variables so you can choose the option that gets the best score. And this is going to make more sense as I keep going. So, simple example. How do you choose what sandwich to eat for lunch, right? You can list all the different sandwiches you have to choose from. You can weigh all the different variables that you're considering, such as taste, nutritional value, etc. and then you actually score those sandwiches by summing up all the weighted variables, and then you choose the sandwich with the best score and you eat it, and it's awesome. So this is basically what that looks like when you actually lay it out in something called a decision matrix. This is kind of like the simplest or most visually intuitive way of talking about cost functions. And this is how you make high-level design decisions in engineering. So here we have our different options: ham sandwich, veggie sandwich, and then here we have our variables: taste, nutritional value. And now what we're going to do is we're going to weight those variables. So I'm going to go ahead and just decide that I think that taste has an importance of 7 relative to nutritional value having an importance of only 4. So then you actually look at your different examples and you're going to score, or sorry, not examples, your different options, and you're going to score those options and you end up with your final score. So for ham sandwich, I decided that it had a taste rating of 8 and a nutritional rating of 5. And then veggie sandwich, I decided it had a taste rating of 6 and a nutritional value of 7. But then since there's a relative weight associated with the variables, taste and nutrition, you actually multiply that weight by the variable and then sum up those values to get your final score. So this 76 is 8 times 7 plus 5 times 4. And then that, based on the assumptions that I made here for my decision, I decided to go with a ham sandwich. But you can make way more complicated decisions here. You can choose like what design to use when you're building your car. Basically lay it out in a big decision matrix like this, where you have, cost, manufacturability, et cetera, as your different variables. So then here's basically what that cost function actually looks like. This is the cost function behind the little decision matrix we just did. You say the cost is equal to, well, I'll go ahead and do this first. So WA is the weight for variable A. So we have some variable A and we're multiplying it by its weight. And then you add that to variable B multiplied by its weight. If you have more variables, you just tag them on here, plus C times WC. And then in this case, we were actually scoring our sandwiches. So it wasn't really a cost function. It was more like a value function. We were saying like the higher score is actually the one we want to choose. But basically what we use this cost function for is to determine our best option. We basically are judging how well our option fits our criteria using this function. So typically you'll have a cost function, and that might actually be in terms of a dollar amount, which is where the name came from, but it doesn't actually have to be broken down to specific dollar amounts. It can just be any arbitrary unit that you could put a dollar price on. So what can we use cost functions for? And basically I'm here to argue that you can make any decision you make essentially is a cost function optimization, no matter how simple or complicated it is. Everyday decisions like what link to click next, you're doing a little cost function like weighing, what links do I have, and how likely does it seem like that's going to bring me where I want to be, and you're choosing it based off that. Design, as I talked about. Machine learning, that's really interesting. Linear regression and error minimization, that's really useful. I'm going to talk about that a lot more. Optimizing simulations, I'm going to talk about that as well. Okay, so choosing from a small number of discrete options like we did in that decision matrix, it's pretty straightforward, right? It was just like, well, this score was the highest, so we're just going to use that. But what if we have a continuous range of options? Like what if we have some variable, some input variable, that we can choose it to be any number, and now we have to decide what's the best number to choose. So this is what that'll typically look like. You'll have, and this is we're changing the variable along the x-axis here, and then we're calling this C of x, cost function of x. So basically, the typical scenario is you're going to have this parabola or some convex kind of function, and that's just your typical optimization where you just need to find what that point is. What's that minimum point? And then that's the x value we're going to use, right? So about 200 is the x value that we want to use there. So some optimization techniques. You can just inspect it like I just did. It was just like, oh, around 200. That's fine. That can work. Analytically, if you actually have the function written out, like cx equals some function of x, you can take the derivative of it, set that to 0, and that's going to give you that point where the slope is 0, right? So the derivative is the slope. Over here, we can see that the slope is negative. Over here, it's positive. So there's exactly one point right there where it's 0, and that's the minimum point. So then computationally, we can use Newton's method. Basically gives you that root where the derivative crosses the x-axis there. And then the really interesting one is gradient descent, which is basically what it does is you start out with some guess, like say we just guessed x value of 400 and we just hit it right there. What gradient descent does is it calculates the slope wherever your guess is, and then it just goes down. So right here the slope's positive, so it knows it wants to reduce the x value to go down. Over here, the slope, like say we guessed right here, the slope's negative, so we know we want to increase the x value to go down. And so you just step it down. You basically drop a ball in the parabola and let it roll to the bottom, kind of. Okay, so what do I really mean like when I say optimization? I just wanted to clarify this. Cost functions give us a method to choose the seemingly optimal choice in complex scenarios. But it's not like this is the ideal perfect value to use. It's just, our models are always going to have assumptions. They're never going to be perfect. But based on what we do know and what assumptions we decide to make, we can use this cost function optimization to get the best inputs for our model. Okay, so before I get into a specific example, I just want to talk a little bit about like what I mean by cost function versus model, because there's a lot of overlap and kind of you can think of the model as being the cost function or the cost function as being the model. So basically, I like to think of the model as a set of assumptions, and that can include variables and actual equations you're using to model your system. And then the cost function itself is just what evaluates the effectiveness of a particular set of input data. And this will make more sense as we go on. So you're going to optimize your model by minimizing your cost function. And the cost function itself is often really straightforward, but the model can be crazy complex. So I'm about to give an example of that. Yeah, simulation. So in this example, the cost function itself is going to be crazy simple, but you'll be able to see that you're still using a cost function optimization to make a decision about a really complicated system. So basically, my methodology for this simulation here, it's a discrete event simulation, which means basically I said, this thing happened at this time, and then this thing happened, and then this thing happened, and I used statistics and stochastically generated values to do it. So basically, my methodology was to develop a cost function. Right off the bat, I was just like, okay, what system am I trying to optimize, and what cost function am I really going to get to there? And so this system is optimizing patient flow through a doctor's office type facility, and my cost function basically ended up being the wait times. But it wasn't just like what do I mean by wait times, right? Like it wasn't just the patient wait time or the physician wait time. You had to take into account both of those variables and then optimize the cost function, which is what I'm going to be talking about. So then you have to track relevant data to actually generate a model which can tell you what those wait times are. And then you actually model the system, do stochastic simulation, and finally you'll get a cost function which you can minimize. So here's my basic cost function. And so what I'm doing here is I'm basically just saying that we think physician wait time is 5 times as important as patient wait time. See? patient wait time, physician wait time, and I'm just saying cost function is equal to 5 times physician wait time plus patient wait time. You know, maybe that's not representative of your, but basically you choose the cost function that is representative of your system. And if you actually could break it down to a dollar value, like you could say every hour of physician wait time is worth this much money, every hour of patient wait time is worth this much money, and then maybe you would have a bunch of other factors like different resources being used in different scenarios. You would want to add all that up in your cost function, whether or not you actually break it down to a dollar value. Okay, so this is how I modeled the system. This is kind of like an overview of the different statistical representations of the model. So basically I assumed a certain number of data distributions, and then I used stochastic number generation to just generate statistically realistic examples. And so basically I could just say, the mean amount of time that a certain appointment took was this, and the standard deviation was this, and then I can use stochastic methods, which you generate a random number and then you put it backwards through, like you put it through an inverse statistics function, like the t-distribution here or the normal distribution here, and it'll actually give you the time associated with that random number. So like under this bell curve we have 100%, right? You would generate a random number 0 to 1, and then that would represent a certain percentage, and then you can map that percentage to the actual value on the distribution here. Does that pretty much make sense? Okay, so basically my process for modeling this patient flow system, it was a dental office facility, and I wanted to take into account the fact that there are all different kinds of appointments you can have, and there are normal distributions associated with how long each of those appointments take, and when a patient arrives relative to when they were scheduled to arrive. So that's the kind of things that I was modeling with these statistics. And so I ended up with this really big, complicated system that took into account all this data that we had to track and all these statistical models. And then finally, I was able to output values to generate my cost function, which is the wait times. So basically what I have is some really cryptic names here, but there was like what kind of appointment is it, and then maybe how many sub-appointments. Like I even took into account, like if you're getting a filling, maybe you have like 3 fillings or something like that. So I wanted to really try to make it realistic into all the different variation you can get there. But so then I generated a expected duration. So you would track that data, right? You would track how long a bunch of different appointments took, and then you would generate a normal distribution based off that. Like you would have a mean value, you would have a standard deviation, and then you can use those stochastic methods to generate statistically realistic examples using that model. So then I had an expected start time, an actual duration, an arrival time, the time that the physician was actually freed, and all that together I was able to generate physician wait time and patient wait time. So basically, if the physician was freed before the patient arrived, then the physician would have to wait for the patient. And so that was one possibility. The only other possibility was that the physician was freed after, like freed from their last appointment after the patient had arrived, in which case the patient would be waiting. So went through all these statistics, all that junk, and finally ended up with a simulation where I could just press go and it would just tell me the wait times associated with whatever variables that I had input to the system. So then basically that gave me the power to optimize any or all of those variables. So I can now actually, like I have those wait times, I can calculate my cost function, I can say, you know, using these input values, this is the cost of my system, and then I can change any one of those given input values. So here, again, we're changing a value, an input value continuously along here, and then keeping everything else constant, just calculating the cost of our system. And you can see it basically gives us that same parabola, convex kind of shape that we had before. It's all jagged because this is stochastic simulation. It's using random number generation. It's not like a perfectly analytical solution by any means, but I wanted to use stochastic because it's like representative of things that can actually happen, and it's kind of a good sanity check to know, like, is this simulation even making sense? But so basically, here's our cost function, and the whole factor value, that's kind of cryptic. What it really represents is a value that it's a value that is multiplied by the difference in the time that you want to schedule a patient to arrive versus when you think a physician is actually going to be ready. So you have the time that you think the physician is going to be ready for a patient, and you could just schedule to have people show up then. But when people actually show up is going to be, as I assumed, a normal distribution with an offset from the time that they're actually scheduled in. So assume that your data tells you that people tend to arrive 5 minutes early, and there's a certain normal distribution on the actual time they arrive there. So basically, what this value represents is that the difference between the mean time that people actually arrive and the time that the physician is expected to be freed. So I was able to optimize the times at which we scheduled people so that it would minimize the cost. It would minimize wait times by optimizing the times you actually schedule people to come in. So all that huge, big, complicated model basically just broke down to this same cost function that I had before. But so then getting into the more complicated side in terms of the actual cost functions, linear regression and error minimization are pretty much the heart of dealing with multidimensional problems. So just to start out, linear regression, basically, you have maybe a scatter plot of data like this, and you want to find the correlation in that data. So you can imagine an x-axis and a y-axis. Here's all your data on this plot, and you want to find the line that best approximates that data. So maybe it's house size versus house price, and you want to be able to just guess how much a house might cost based off its size. Then you would use linear regression to determine this line, and you would just assume, if it's right here, go up to the line, and then go over and find that cost. And that'll give you a reasonable approximation. So that's basically what linear regression is all about. But the way you actually do it is with a really, really useful and common cost function optimization technique, which is error minimization, specifically sum of squared error minimization. So here's our cost function, and this symbol means the sum. So basically, what we're doing here is for each of these points, one second. Okay. So in linear regression, we have a model like this. This is pretty much like your simplest, just basic line model, right? Y equals bx plus a, or mx plus b, if you're used to that. So these are our inputs. B and A are our inputs, and we want to optimize those so that our line fits the data as best as possible. We're going to start off with just a pretty arbitrary guess, say this red line, you can see it doesn't really fit the data. The blue line's where we're going to end up. The red line's just like okay. So you start off with a guess like that, and then you use sum of squared errors to determine how well that line actually fits your data. So what we're doing here is for each one of these data points, we're taking the difference between where that point is and where our line guesses the point should be. So that's the difference right there, that's the difference right there, that's the difference right there. You take all those differences or all those errors, you sum them up, and that tells you the cost of your input choices. So the one caveat there is that if you just sum up all these errors, a lot of them will cancel out since these ones are going to be negative and these ones are going to be positive. So what we can do instead is just square it. That'll guarantee that it's never gonna, that all the values are gonna be positive. And it turns out, I mean, you could just take the absolute value, that works too. But it turns out that the cost function, the optimal value for the cost function is gonna be the same whether you square it or not. So people just square it so that they're not dealing with the cancellation. So then what we're gonna do here is essentially use gradient descent. But instead of just varying one variable as we were before, we're going to be varying both of these variables. So we're going to be tracking, as we change our guess line, as we move it up, change that A value, calculate the cost function every time we do that. And if it gets better, then we're going in the right direction. If it gets worse, go in the other direction. And then the same thing with changing the actual slope, which is that B value. We're calculating that cost function, and then as we change it, we're evaluating, is this making it better? And if it is, you keep going in that direction. And that's how you optimize in multiple dimensions. So basically what it ends up being is you're doing the same convex optimization that we were doing before where we just had the parabola, but now we're doing it in multiple dimensions at the same time. So instead of dropping the ball on just that parabola and letting it roll down, we're dropping it in this case, we have two inputs. So we have like a two-dimensional space here, and we're dropping the ball in this, we're dropping the ball in this bowl and letting it roll to the bottom of the bowl. So we're letting it step down in 2 dimensions instead of just 1. But if your model is more complicated, say maybe you have y equals cx squared plus bx plus a, then you have another variable you need to optimize. And basically what it would do is just add another dimension to this, which is really hard to visualize, but it works exactly the same because we're essentially looking at each of the dimensions individually, using partial derivatives to get the slopes of each dimension individually. So it ends up being the exact same problem, you just have to do it for each of the dimensions that we were doing it. Okay. So then some of the problems you come across doing stuff like this, well, this is basically what I've already been talking about. Just uses partial derivatives to step down in all the dimensions. But then here's an interesting case where, we have 2 different guesses here, and they're really close, but they actually end up giving us different answers. So if we have a complicated problem, we can end up with this situation where there are a lot of local minimum. So you can see this is the minimum point if we were just looking at this area. But if we look at this whole thing, maybe this one's lower. And we want to get that lowest point on our graph. But gradient descent only guarantees a local minimum. It doesn't guarantee that you're going to get the lowest point in, if you make your space bigger. So to deal with this, you can just use guess and check. I mean, you could just drop a value at, each one of these points on the grid and just whichever one's best, just, great, that works. Or you can use good heuristics, like maybe you have some professionals in the space dealing with whatever system you want to optimize, and they have a really good idea, like it's probably going to be around here, and then you can kind of cut down your system to being only a subset of this bigger problem, and then find your global minimum there. And then another really interesting way of approaching this is called simulated annealing, where the way I like to think of it is basically like you throw a ball really hard. Instead of just dropping it, you throw it, and it just kind of like bounces around and finally ends up at one of the minimum. Hopefully it's the global minimum. It's more likely to be lower than any arbitrary guess. Okay. So essentially, any decision can be made with cost function optimization, even super complicated ones. How are we doing on time, by the way?
38.
Okay. Okay, so super complicated decisions can be made with cost functions. And this is where we get into neural nets. So basically, what a neural net is it's a layered cost function. When you actually have your trained neural net and you're going to use it to make a particular decision, it's essentially a layered cost function being used to make that decision. So instead of just having sum of squared errors or something like that, you actually have multiple layers here where, I wish you could see that better, but basically the value, you start off with some inputs. So you have values right here. Let's just assume they're a number from 0 to 1. And then you have a whole bunch of weights. So all these arrows are weights. So when we calculate this value here, we're going to sum up this value times this weight plus this value times this weight plus this value times this weight. And we do that similar process for each of these points in this hidden layer here. And then we could have any number of layers in this neural net, but basically we've done a cost function evaluation on each one of those already. And now we're going to do the same thing again. When we actually calculate our output values, we're going to multiply this by its weight plus this by its weight plus this by its weight plus this by its weight. So that's how a neural net determines whether or not your input, if it's a classifier, right? If it's an image classifier and it was trained to recognize dogs, then you put in all the values of the pixels here, and then over here you're going to have like a dog output. And if it's like close to 1, then you're confident that it's a dog. And that's pretty much how it works. So then when you're actually training it to recognize dogs, what you need to do is choose what all these weights are going to be. And that is basically where the gradient descent comes into play. But it's not just gradient descent anymore, since we have a layered cost function. It's called backpropagation. So basically, what you do when you're training it is you actually tell it what you think it should be. So we put in we have an image of a dog, and we put in all the pixel values over here. And then over here, we're going to say, this should be a 1, because this is a picture of a dog. We want the neural net to tell us 1 on this node, because that's what we're choosing to mean that this is a dog. So what you do is you have it completely untrained. You just have guesses for all these weights, and you just let it calculate its cost, and then based on the actual difference of whether it thinks it's a dog versus whether you're telling it's a dog, you take the difference of that value, and that's basically your error. So that's what you're going to minimize now. And to minimize that, you're going to use something really similar to gradient descent, where you step up or down all of these weights based on whether this error was positive or negative. based on how big the actual error was, you're going to step all of these weights so that next time you give it that same image, it'll give you a slightly better answer. And so that's how you train the neural net, is you give it a bunch of pictures, tell them whether or not they're dogs, and then slowly over time it'll get better and better at recognizing what a dog is. So yeah, same stuff, just way more complicated.
So that error function, needs to be differentiable, right?
Sure. Yeah, I'm not going to get into details like that. It's too much fun. Okay. So, and then I just wanted to talk a second about practical neural nets, because, this might be the cost function, and that might be straightforward enough. Like, you end up with just this cost function where you just calculate this value and it'll tell you what you have. But actually training the neural net and setting up the logic to break the problem down to something that you can solve with the neural net it's really complicated. I'm sure Jeff knows way more about that than I do. I haven't really built my own neural nets from top to bottom like that. But there are really cool things out there that do that part for you, and you can just kind of black box neural nets, and it's awesome. And one of them is IBM Watson. So IBM Watson is really cool because it is trained off of Wikipedia. So it kind of already has all of the context of Wikipedia, and it lets you set up your own little neural nets. Like, say you want to do a natural language classifier. It'll let you use its API, and you don't even have to give it a huge training set, because it already kind of has context. It already has some intuition about what all the concepts that humans understand mean. So you can give it a pretty small training set, and it can give you a really nice, effective classifier. So I just wanted to give a specific example of that. They have this awesome API with a suite of 14 different cognitive tools you can use. And one of my favorites is the natural language classifier, which I actually was working with for a while this summer when I was working with Engager. So I don't know if any of you guys know what Engager is, but basically it's a interactive video platform. So the solution that we wanted here was to have users come in and just type a question in natural language, like what's the cost of this product, and then have the most appropriate video served up to them. So they wouldn't have to click through and find the video themselves. They could just ask a question in natural language. And that's what this natural language classifier does, is you give it a set of questions, like what's the cost, how can I use this, stuff like that. You give it a whole bunch of questions, and you tell it what video you want those questions to lead to, and then it'll give you this classifier which can take completely different questions from the ones that you had given it, but it's using IBM Watson, so it understands the context of what those questions actually mean, and it can still give the most appropriate video using that technology. So that's really cool. If you actually want to implement something, like the iPhone Siri or some of these cognitive technologies, you can do that now with IBM Watson. All right, thanks guys. That's my talk. Questions, Brett?
You guys have any questions? Kick me off.
It's kind of a lot of stuff. Simulations, cost functions, AI.
So when you were talking about dropping the ball down,
Yeah.
what in actuality does that mean? What does that look like?
So what's actually going on, maybe like in the bowl?
Yeah.
So what's actually going on is you're just choosing some value for B and A, right? And then you're actually taking the derivative of the cost function at that point. And you're taking the partial derivative with respect to b and the partial derivative with respect to a. So that'll actually tell you the slope of the cost function with respect to both of those variables. Then you can change those variables so that you're moving down the slope. And that's what I mean by letting it roll down. You're really stepping down incrementally. You let it calculate the slope, then you step it in all dimensions at the same time. Then you recalculate the slope, step it, and just repeat, step, 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 step. And eventually you'll get to a point where it's not really changing. It's just kind of like, you know, it's at the minimum there. And I mean, simple like gradient descent algorithms are really easy to implement yourself. Like if you know just a little bit about how to take a derivative and how to just make a decision which direction to step based on whether it's positive or negative, that's kind of all it takes at the base level.
Anybody else?
I know a place I've used a lot of the kind of cost scoring functions recently is like Elasticsearch. So if anyone uses a search algorithm or uses Elasticsearch or Lucene or any of those, effectively you can get access into the cost function and build your own for different pieces and parts to make a better search for whatever your content is about.
Cool.
Also, most of this is one-liner stuff in Python, if you get into it. So
Python is cool.